So about 5 years ago, I got the itch to build a house for myself. I was living in a little townhouse in Cambridge, Massachusetts. The idea was to build a house in the country somewhere as a gathering place for family and friends. So the main space of the house, there's a big living area that has the dining area and an open kitchen. Kitchen is set up so that it's easy for 6 or 8 people to be fixing dinner at the same time, because that's what we do. I had designed lots of houses back in the 70s and 80s with an emphasis on energy efficiency. I was doing a lot of passive solar designs and some designs even with photovoltaics back then. I wanted something that was going to fit the land, that wouldn't be ostentatious, that would be simple and well detailed, and a house where the design of the house really reflects the way that the house is built. As I looked at all the latest things in energy conservation, one of the things that I found most interesting was a concept that is sometimes called perfect wall construction. And I thought that was interesting because it's a great way of dealing with the building science of a wall. I think many people think walls are very simple, but they're really complicated. They have to hold the building up. They have to perform thermally, they have to keep the draft from blowing in, and they have to keep moisture from moving through the walls. So there's a bunch of complications, and the more insulation we put into buildings, the more issues we have with vapor transfer. So the thing I liked about Perfect Wall is it really deals with all of those things. I think it's called Perfect Wall not because it's perfect, but because it works in all climate areas, every place across the country. So basically the way this house is built is there's a 2x6 frame, which would be like pretty much the way every house is built. Then that gets sheathing on it. But then one of the interesting things here is we do a continuous air-water vapor barrier that goes all the way from the foundation up the walls and continuously over the roof and back down the other side. So we really create a really airtight enclosure that prevents air movement and water movement and vapor movement. Then on the outside of the building is where most of the insulation goes. So there are 6 inches of rock wool insulation on the outside of the building. That's held up with strapping that is screwed into the wall, vertical strapping. Then there's horizontal strapping on top of that, and then vertical siding on top of that. That gives us a nice airflow and a drainage plane, so any water that gets in, which it inevitably will, has a way of either going back out as vapor or draining down the cavity behind the siding. Then on the inside of the house, we fill that 2x6 stud wall cavity with blown-in fiberglass insulation. And this creates a nice situation where you have a vapor barrier that's in the middle of the wall, so you can run plumbing through and you can have electrical fixtures, and you're never going through the vapor barrier as it would be if you tried to put the vapor barrier on the inside of the construction. The walls are R40 something, and the roof has a little bit more of that rock wool on it, so we're probably up to R60 for the roof. All the windows are triple glazed, so they're well insulated, and all the windows are sealed back in to the air and water vapor barrier. So it creates a really efficient envelope. And then when you do that, you do need to control the air that's coming in the building, So it's really better to control that air and exhaust air in a meaningful way or an intended way rather than letting it just kind of leak and blow into the building. So one of the key things is an energy recovery ventilation system. So that's a system that takes stale air from the house, exhausts it to the outside, and pulls fresh air in from the outside, but runs both of those streams of air through a little exchanger. So it pulls the heat out of the air that's expelled in the winter and the humidity and puts it back into the air that's coming in with an amazing degree of efficiency. And that is a separate system that then is ducted to each one of the rooms in the building. So that means there's great fresh air and air quality at all times. Really helps promote comfort. No drafts. Everything is controlled in terms of how air comes into the building. Then the next things we do in terms of energy is we want the house to be completely electric and everything to be as efficient as possible. The house has 2 ducted air source heat pump systems, sometimes called variable refrigerant flow. That's a very efficient system because what a heat pump is doing is it's moving heat. It's not creating heat. So if you put 1 unit of energy in, you're getting like 4 units of heat for that 1 energy that you put in, because it's pumping the heat from the outside into the building in the winter and pumping the heat from the inside to the outside in the summer. Then we have efficient electric appliances. So we have an induction cook stove, electric oven, a heat pump water heater, and a heat pump dryer as well. So we try to have everything be as efficient as possible. We have a solar system on the roof that provides more energy than the house itself actually uses. Under normal conditions, it draws about 3 kilowatts. So that's 3,000 watts. That is about the equivalent of 2 hair dryers to heat the whole house, and we're about 2,500 square feet. I have 4 bedrooms. The outside of the house, I was really interested in doing something that was low maintenance. And there's an interesting product that's been around for a while in Europe that's beginning to gain traction here, and that is thermally modified wood. So the house is clad with a thermally modified poplar siding. But what they do is they take the wood, in this case the poplar, and it goes into a big oven, and it's cooked, I think it's at about 400 degrees for like 20 hours. And what that does is it cooks the moisture out of the wood, it cooks the oils and the sugars out of the wood, and then they introduce moisture back in and let everything cool down. And when they do that, the result is a wood that doesn't have any sugars or oils in it, so it's rot resistant because there's nothing for molds and things to eat. It's resistant to any kind of termites or bugs because there's nothing edible that's left in the wood. And the wood itself turns this beautiful kind of mahogany color, and it's that consistent color all the way through the wood. The other advantage is because it's all been dried out and has a good consistent amount of moisture that's put back in. It's milled after it's heat treated, and that means you get pieces of wood that are very straight, that remain very straight. In the summer, I have a screen porch, and there's an accordion-style door that I can open up so the porch is completely open to the inside in the summer. And so the whole house then has great cross ventilation. It feels like the whole house is really a porch and you're outside. When I was an architecture student, I was generally familiar with Frank Lloyd Wright, but it wasn't until after I graduated and I visited the Pope Leahy House, which is outside of Washington, D.C. And that's an early Usonian house that Wright built. Small, very modest house. It's on a concrete slab with wood walls, very, very modestly sized, but beautifully detailed. And it was really, for me, it was a very moving experience when I went into the building. And that really piqued my interest in Frank Lloyd Wright. Studying him and his life has been something that I have enjoyed doing now for many years. He has been an influence on many of the buildings that I've done. This house, for instance, you wouldn't look at it and think that it has very much in common with Frank Lloyd Wright, unless you look closely. Wright never liked to plan things orthogonally on the site, so he would pretty much always rotate them. And one of the things we did here was to rotate the house about 30 degrees to the shoreline. So it's just a nice way to site it. It's, I think, a way of saying that it's what's important is the way the house relates to the site itself, not necessarily all the sort of man-made roads and property lines and things that we impose on the land. I did want to open up the house as much as possible, as Wright would do. Wright loved to blow away the corners of his building, so he would often have windows where a single sheet of glass would go to the corner and he'd have mitered glass, so there would be nothing supporting the corner of the building. Today, with triple glazed glass, you really can't do that very easily. So I did kind of the next best thing, which was to run the windows to the corner, but do as small a post as I could. So we do that pretty much in all the rooms in the house. And that really opens up the feeling of the interior rather than having a window that's punched into the wall. I've always admired the work of the early modernists who would build furniture for their houses out of the same materials that they built the house out of. So I did furniture here out of birch plywood that has kind of that same aesthetic. I did the dining table and the coffee table and the side tables, and the beds and the side tables in the bedrooms are all made from birch plywood specifically for the house. For a number of years, I've been doing sculptures that try to capitalize on the unique characteristics of birch plywood. I love the way the edges look when you can see all the laminations in the plywood. I think part of the appeal is I like the honesty of the product. When I see plywood, I like to know that it's plywood and not pretend that it's some kind of solid wood by edging things. The window and door casings are all done with plywood, but we turned the laminations to the face. So when you see the door, what you see are all the laminations of the plywood. I think it contributes a lot to the warmth of the interiors, and I think it has a nice richness to it.